On January 15, 2022, weather stations across Alaska registered barometric pressure spikes, equivalent to a major storm system's materializing overhead. There were no storms, no fronts within 800 kilometers. The pressure anomalies moved in a circular arc at 1,100 kilometers per hour, radiating from a point thousands of kilometers to the southwest. That same morning, tsunami sirens activated along the Peruvian coast near Lima. Waves struck the port of Callao. No earthquake had preceded them. In Fiji, windows rattled from sustained acoustic pressure rolling across the islands for minutes. In New Zealand, residents across both islands reported sonic booms and called emergency services. In Japan, barometers spiked by 5 to 8 millibars under clear skies. Emergency services received hundreds of calls across multiple countries. For 6 hours, these anomalies were treated as unrelated. The source was a volcanic island in the South Pacific, Hunga Tonga, Hunga Haʻapai. It had detonated with energy equivalent to 10 to 15 megatons of TNT, comparable to the largest nuclear weapon the United States ever tested, through a mechanism that had no precedent in modern volcanic monitoring. The shockwave punched through the ocean's surface, through the troposphere, into the stratosphere and beyond, then wrapped around the planet and kept going. Every barometric monitoring station on Earth recorded its passage within 18 hours. The eruption registered on instruments in every country simultaneously, not as regional effects rippling outward, as a single coherent wave circling a planet. Hunga Tonga, Hunga Haʻapai had been largely ignored for decades. 2 small uninhabited signs marked the rim of a submerged volcanic caldera. Volcanic rubble above the waterline, the main vent 150 meters below the surface. That depth is what made it dangerous. At a depth of 500 meters, water pressure contains eruptions before they reach the surface. At the surface, a land-based volcano allows seawater to flood the magma chamber gradually, limiting explosive contact. At 150 meters, water pressure is sufficient to keep water liquid far above its normal boiling point. Superheated, under pressure, in direct contact with magma at over 1,000 degrees Celsius. When that pressure releases, the water doesn't transition to steam gradually. It undergoes an explosive phase change. The expansion ratio of water to steam at atmospheric pressure is approximately 1/700 to 1. At 150 meters depth, the confinement multiplies that force before it can dissipate. The result is classified as a phreatomagmatic eruption, a steam-driven detonation rather than a lava-driven eruption. The caldera's geometry compounded the mechanism. Hunga Tonga's horseshoe shape concentrated explosive force vertically. Eruptions since 2014 and 2015 had partially filled the caldera with new volcanic material, creating a structural cap beneath which pressure could accumulate without a gradual release pathway. The geometry converted a moderate magma chamber into a confined detonation chamber with no pressure relief valve. The process accelerates. Seawater contacts magma, flashes to steam, and fragments the magma into fine particles. Each fragment exposes a fresh surface to seawater. Each contact generates more steam, more pressure, more fragmentation. The reaction does not stabilize, it cascades. Nuclear engineers encounter the same dynamic in reactor accident scenarios. Liquid coolant contacting overheated fuel generates steam faster than pressure relief systems can respond, shattering the fuel and accelerating the reaction. Hunga Tonga operated on the same physics. The energy did not come from magma chemistry. It came from water phase change at volcanic temperatures and oceanic pressures, and the shallow submarine position gave the eruption access to an essentially unlimited coolant supply. The 2014 and 2015 eruptions had added a final component. New volcanic material filling the caldera created a structural seal, a cap beneath which pressure could build with no gradual escape pathway. Between January 13th and 15th, 2022, each small precursor eruption partially relieved and then repressurized the chamber, each cycle weakening the cap further until the seal failed catastrophically rather than allowing incremental release. The eruption that monitoring agencies cataloged as the main event on January 14th was not a conclusion. It was the cap giving way the first time. The monitoring system saw activity. They did not see what was coming. On December 20th, 2021, Hunga Tonga produced a moderate eruption that built a new volcanic cone within the caldera. Satellite imagery showed fresh land connecting the two islands. Tonga Geological Services noted it. On January 13th, Ash emissions were visible from Tonga Tapu, 65 kilometers away, within normal parameters for an active volcano in the region. On January 14th at 4:20 p.m. local time, a significant eruption produced an ash column reaching 15 kilometers. Local tsunami warnings were issued, and the eruption lasted 30 minutes, then subsided. Monitoring agencies recorded it as the main event and downgraded warnings overnight. The January 14th eruption was not the main event. It was a structural failure beginning. Phreatomagmatic eruptions do not generate the seismic precursors that magma-driven eruptions produce. Traditional volcano monitoring detects magma moving through rock. Friction generates earthquakes, swarms, and harmonic tremors building over days or weeks. Steam pressure builds differently. Water infiltrates fractures, contacts heat, and expands into void spaces behind cooling rock and volcanic debris. No magma movement, no distinctive seismic signature. Pressure accumulates silently. Hunga Tonga had no ground-based seismic stations. The islands were uninhabited. Monitoring depended on satellite observation and distant seismographs calibrated for large tectonic earthquakes, not the subtle fracturing of a pressurizing steam chamber. January 15th, 5:10 a.m. local time. The main sequence initiated. Satellite infrared sensors registered a sudden brightening as the first explosive breach occurred. By 5:15 a.m., the eruption column was rising at velocities exceeding 400 meters per second. It reached 58 kilometers altitude within 8 minutes, through the stratosphere and into the mesosphere, the layer where meteors ablate. The explosive phase lasted 10 to 12 minutes. In that window, the volcano ejected an estimated 0.4 to 1 cubic kilometer of fragmented rock and pumice, injected 146 billion kilograms of water vapor directly into the stratosphere, and generated an atmospheric shockwave with energy between 10 and 15 megatons TNT equivalent. The eruption column generated its own electrical storm. Ash particles at high velocity collided, stripped electrons, built charge separation faster than it could dissipate. Lightning began at 5:12 a.m. Within 3 minutes, the discharge rate reached 600 strikes per minute. At 5:30 a.m., the submarine fiber optic cable connecting Tonga to Fiji severed. Tonga went offline. For approximately 5 weeks, external communication depended on satellite phones and amateur radio. By 6:00 a.m., the primary explosive phase had ended. Satellite imagery from January 16th shows the island that had connected Hunga Tonga and Hunga Haʻapai no longer exists. Approximately 40% of the visible landmass is absent. Post-eruption bathymetrics survey explosion had excavated the seafloor below the pre-eruption baseline. The caldera had deepened rather than collapsed inward. The energy required to vaporize and disperse millions of tons of rock in 10 minutes places the explosion in the same energy category as thermonuclear weapons. Volcanic ash covered Tonga Tapu to depths of several centimeters, contaminating freshwater sources and destroying crops across the island. The ash was fine enough to remain suspended in water systems for weeks, rendering tank water undrinkable without filtration. Agricultural land across the island required clearing before replanting was possible. Coral reefs in the surrounding waters were smothered by volcanic sediment settling out of the water column in the days after the eruption. The marine ecosystem impacts extended across the Tongan archipelago and were still being assessed months after the event. The acoustic effects extended well beyond the immediate destruction zone. At distances of 50 to 80 kilometers, witnesses reported feeling the eruption as much as hearing it. Pressure in the chest, nausea, and disorientation, consistent with infrasound exposure. Infrasound is acoustic energy below 20 Hz, below the threshold of human hearing, but within the range the human body registers as physical disturbance. It penetrates structures, travels further than audible frequencies, and produces physiological effects independent of perceived loudness. The eruption released substantial energy in this range. Its effects on the body at distance were documented across multiple survivor accounts from islands in the Haʻapai group. The waves hit Tonga Tapu, Tonga's main island, 65 kilometers south, within minutes of the eruption's peak. Water surged up to 15 meters above sea level in certain coastal areas. On Mango Island in the Haʻapai group, closer to the source, waves erased settlements. 2 confirmed deaths on Mango. The total confirmed death toll across Tonga was 4 to 6, though some remote communities remained unreachable for weeks. The low number was a function of timing and geography. The eruption occurred at dawn when many communities were already awake. The initial explosion was visible and audible from inhabited islands, and most of Tonga's 100,000 residents live in Tonga Tapu, rather than the smaller islands nearest the source. The tsunami warning system failed, not through equipment malfunction, but because the eruption generated a wave type the system was not designed to detect. Standard tsunami generation. An underwater earthquake displaces the seafloor vertically, shoves the water column upward, and the displaced water propagates outward as a wave at roughly 800 kilometers per hour in deep Pacific water. Seismometers detect the earthquake within minutes. The time between detection and wave arrival provides the warning window, typically 40 minutes to several hours depending on distance. The entire system depends on seismic detection as the trigger. Hunga Tonga generated two simultaneous wave mechanisms. The first was conventional. Underwater explosions and caldera collapse displaced water, producing waves that propagated at normal ocean speeds. These attenuated predictably with distance. The second had no precedent at this scale. The atmospheric shockwave, traveling at 100 kilometers per hour, faster than ocean-speed tsunami waves, crossed the ocean surface and pushed downward on the water with a force of 5 to 10 millibars across hundreds of kilometers. The ocean surface deformed under atmospheric pressure. A depression formed, traveling at the speed of sound in air. When the pressure wave passed, the water rebounded. The result was a meteotsunami, a tsunami driven by atmospheric pressure rather than seafloor displacement, traveling at atmospheric speeds. Meteotsunamis occur regularly at a small scale, generated by fast-moving squall lines. Typical heights, 0.5 meter to 2 meters, affecting coastlines over distances of 50 to 200 kilometers. Hunga Tonga's shockwave generated a meteotsunami that maintained coherence across ocean basins and struck coastlines 10,000 kilometers from the source. At Fiji, 750 kilometers away, tide gauges registered wave arrival 40 minutes after the eruption. The shockwave had already crossed the distance before the seismic signal could provide a warning trigger. The waves arrived faster than the warning system's detection mechanism could respond. Japan, 7,000 kilometers distant, recorded tsunami waves exceeding 1 meter arriving approximately 7.5 hours after the eruption. Japanese warning protocols, designed around seismic triggers, issued alerts only after waves were already striking the coast. Peru recorded 2-meter waves at Callao approximately 10 hours post-eruption. The atmospheric shock wave had crossed the Pacific, traversed the Andes, and when it reached Peru's Pacific coast from the landward direction, generated pressure variations sufficient to produce measurable tsunamis. The La Pampilla oil refinery suffered structural damage. Approximately 900 barrels, about 1.9 million liters, of crude oil spilled into coastal waters, Peru's worst ecological disaster on record at the time. 2 people drowned in Lambayeque. No earthquake had preceded the waves. Existing models had not predicted meaningful tsunami risk at that distance. The Pacific Tsunami Warning Center issued initial advisories for Tonga within minutes of the eruption based on the caldera collapse and underwater explosions, generating conventional displacement waves. Those advisories were accurate for the immediate zone. What they could not account for was the atmospheric mechanism generating waves simultaneously at distances beyond the conventional tsunami range. The warning center's models did not include atmospheric pressure forcing as a tsunami generation mechanism at transoceanic scales because no event had demonstrated it at that scale before. The gap between the issued warnings and the actual wave impacts at Peru, Japan, and the U.S. Pacific coast represented the difference between what the detection infrastructure was built to find and what the eruption actually produced. The atmospheric shock wave that crossed the Pacific and generated tsunamis in Peru was the same pressure wave that registered on weather stations across Alaska, rattled windows in Wellington and Sydney, and spiked barometers across the Caribbean. It completed one full circuit of the planet in under 18 hours. Then it circled again and again. Global barometric networks tracked it, completing 4 confirmed circuits over 72 hours. The oscillations weakening progressively as energy dissipated into the atmosphere. Scientists called it a LAM wave, an atmospheric pressure wave that travels horizontally along the density boundary between the stratosphere and troposphere. The physics. Explosive energy injected vertically into the atmosphere at sufficient speed and magnitude couples with the density. Differential between atmospheric layers. Sound waves traveling along this boundary reflect off it rather than dispersing outward, maintaining coherence over planetary distances. Hunga Tonga's column reached the stratosphere at 400 meters per second and deposited energy directly into the layer boundary. The wave that resulted circled Earth rather than dissipating. The global sensor network recorded the wave's properties in unprecedented detail. Barometers registered pressure variations of 2 to 10 millibars as it passed, comparable to the arrival of a strong weather front, appearing instantaneously under clear skies. Microbarometers at infrasound monitoring stations tracked the wave's precise travel time between continents, allowing researchers to calculate its speed and energy retention across successive circuits. Seismometers designed to detect ground motion registered the wave as it compressed the surface itself. The same event appeared simultaneously in meteorological, seismological, oceanic, and satellite data, a single source producing signals in every monitoring network simultaneously. LAM waves had been documented twice before in the instrumental record. The 1883 Krakatoa eruption produced one, reconstructed from barograph records across Europe and Asia. Nuclear weapons tests in the 1950s generated smaller examples. Hunga Tonga was the first event of this type captured by complete global sensor coverage. Thousands of barometers, microphones, seismometers, and satellite instruments simultaneously recording a single atmospheric disturbance crossing every point on the planetary surface. The wave registered in Antarctica. It registered at the theoretical antipodal focus point near Algeria, where waves traveling east and west converged after completing half a circuit and were briefly amplified. Every nation on Earth recorded it. The eruption demonstrated something that atmospheric physics describes theoretically, but planetary experience rarely confirms. Earth's atmosphere operates as a unified resonance system. A disturbance at one point propagates globally as a coherent wave through the continuous fluid envelope surrounding the planet. The atmosphere does not segment at continental boundaries. It rings as a whole. The 146 billion kilograms of water vapor Hunga Tonga injected into the stratosphere created a climate effect with no precedent in the volcanic record. Standard volcanic climate impact runs like this. A major eruption injects sulfur dioxide into the stratosphere, which converts to sulfate aerosols, reflective particles that scatter incoming sunlight before it reaches the surface, cooling the planet temporarily. Mount Pinatubo in 1991 ejected 20 million tons of sulfur dioxide. Global temperatures dropped approximately half a degree Celsius for 2 years. Hunga Tonga released an estimated 400,000 tons of sulfur dioxide, less than 5% of Pinatubo's output. The sulfate cooling effect was negligible. The water vapor injection reversed the expected outcome. Stratospheric water vapor is a greenhouse gas. It traps outgoing infrared radiation. In the troposphere, water vapor cycles rapidly. Warmer air holds more moisture. Moisture precipitates within days. The cycle constrains itself. In the stratosphere, there is no precipitation. Water injected there accumulates and persists. The stratosphere at 58 kilometers altitude is effectively a desert. Normal water vapor concentrations are measured in parts per million. Hunga Tonga increased global stratospheric water vapor by approximately 10% in 12 minutes. That water remains, trapping heat for years. Early climate studies published between 2022 and 2024 estimate Hunga Tonga's net contribution as a warming of 0.01 to 0.04 degrees Celsius, with the effect persisting until the vapor disperses, projected between 2027 and 2030. The range reflects uncertainty in the interaction between the minimal sulfate aerosol cooling and the water vapor greenhouse warming. The direction is consistent across models: warming, not cooling. A volcanic eruption that warms rather than cools had not been observed at this scale in the modern instrumental record. The water vapor injection also interacts with stratospheric ozone chemistry. Initial studies detected localized ozone depletion in the months following the eruption, as water vapor participated in reactions that produce ozone-destroying compounds at stratospheric temperatures. The long-term effects appear limited as the plume disperses, but the eruption provided a natural experiment in stratospheric photochemistry at scales impossible to replicate in laboratory settings. Scientists are observing ozone, temperature as the water vapor gradually descends through the stratospheric layers toward the troposphere. The eruption was relatively modest by volume of ejecta. It achieved disproportionate atmospheric impact through the combination of explosive efficiency and unlimited water access. The power came from mechanism, not magnitude. That distinction matters for the submarine volcanoes in the Pacific sitting within the phreatomagmatic depth window, most of them unmonitored. The pressure wave that rattled windows in Wellington and spiked barometers in Alaska was the same event that generated tsunamis in Peru, severed a fiber optic cable in the South Pacific, warmed the stratosphere for a decade, and injected more water vapor into the upper atmosphere than any documented event in the modern record. Every instrument on the planet recorded it. Most weren't designed to understand what they were measuring until after the wave had already passed. Hunga Tonga exposed specific gaps. Submarine volcanoes at the phreatomagmatic depth window that produce minimal seismic precursors before detonating. Atmospheric pressure waves that generate tsunamis faster than seismic-based warning systems can respond. Eruptions that warm the stratosphere rather than cool it. Following the event, the Pacific Tsunami Warning Center initiated a review of warning protocols to incorporate atmospheric pressure forcing as a tsunami trigger. Several Pacific nations began deploying additional oceanic pressure sensors. The monitoring infrastructure built around land-based magma eruptions and earthquake-generated tsunamis did not fail through malfunction. It failed because the event it was measuring was a different type of event than the systems were designed to detect. Approximately 1.0 submarine volcanoes in the Pacific sit within the 100 to 200 meter depth range that makes phreatomagmatic eruption possible. Most are unmonitored. The LAM wave that circled Earth 4 times in 2022 is still theoretically detectable in the long-period atmospheric record. The next one will be 2, in retrospect, after the shockwave has already completed its first circuit.